Well, hello YouTubers, electronics enthusiasts. Welcome back to my channel. Mike here. Once again, we're working with the JAZ80 breadboard Z80 retro computer that I built. And it's time to start the upgrades on this. This is the level 0. And we want to start upgrading this to level 1, where we're going to have a lot more bells and whistles on it. Let me fire it up here. And right now, all we've got for inputs is some dip switches over here, and all we've got for outputs is a set of LEDs over there. As we upgrade this to a more capable computer, it's going to have a lot more inputs and outputs. I want to have serial I/O on it. I want to have better parallel I/O. I want to do a lot of other stuff to this machine, but we're going to take baby steps. We can't do all that in one video either. It's going to take quite a while. I'm going to have to write some code too to test all the changes as I make them, and I'll walk you through the code I'm going to write. And like I said, that's way too much for one video. We're going to take baby steps. So today, what I propose to do is we're going to start out by taking out the 555 timer over here. I'm not actually using it right now. I am on the fast 4 megahertz clock. We're running the Z80 at its full 4 megahertz clock speed. As you can see, the M1 light looks like it's on constantly. It's not. It's just going very, very fast. So, not really using the 555 clock source anymore. We're going to take the training wheels off this machine a little bit. So I want to pull this out. I need the board real estate up in this area, so I'm going to move the 4 megahertz clock down here in the space where the 555 timer was. And also, I would like to move this reset button, maybe bring it down here towards the edge of the breadboard down here, and free up a little bit of space up here. But the main thing we need to do today, and that's probably going to take up the bulk of the video, is I need to rewire this socket right here. The zero insertion force socket I have that I plug the EEPROMs in with the firmware in them. When I laid this out, I only wired it up for a 2816 2K by 8 EEPROM. Okay, and I want to use 28C 256, which is a 32K by 8 EEPROM, even though we're only going to use the bottom 16K of it. The pinout's quite different, and I made kind of a mistake when I wired this up. That's not going to make it so easy to rewire it, so we'll get into that. But I think we'll start off with something simple. I think we'll just remove the 555 timer and move the 4 megahertz clock down. Make sure that works. Move the reset button down. Make sure that works. And then once we're good and warmed up, we'll move on to the more complex problem here of rewiring the EEPROM socket, okay? And I'll give you a look at the schematic and show you what I'm talking about over here with this. Okay, so what we need to tackle today is I want to remove this 555 clock oscillator circuit. We're not going to be using the slow clock anymore with this computer. We've got it up and running to the point where we don't really need the slow clock for debugging anymore, I don't think. So we're just going to go with the 4 megahertz clock from here on out and run the processor up here at its full 4 megahertz speed. We're going to take some of the training wheels off this computer. So we're going to pull out the 555 timer chip and all of its associated circuitry, and I'm going to move the 4 megahertz oscillator from where it is now up on the 3rd tier of breadboards down to the real estate that's been taken up by the 555 up till now, right next to the Z80 processor. So if you look at the level 1 schematic, the level 1 schematic shows we don't have the 555 in here anymore. We've got the 4 megahertz, and we've got another oscillator in here which I don't think we'll get around to installing today. Probably in the next video we'll do. If there's time in this video, because this video could get fairly long and cumbersome, we might tackle the I/O decoding problem that we've got. We need to upgrade the I/O address decoding, and that's all buried under this big tangle of wires here, unfortunately. So, yeah, we'll see if there's time for that today, or maybe we will roll it into the next video. Okay, let's get started. First thing I'm going to do is turn it off. I'm going to unplug it. Okay, and then I'm just going to start pulling parts out. We don't need any of this stuff over here. This is all stuff for the 555 timer circuit over here. So we can just pull all this stuff out. Let's see, we don't need that. We don't need that. We don't need the 555 anymore. That can come out. Let's see, we don't need any of these short jumpers here. Yeah, well, we'll have to reuse a couple of them, but for the 4 megahertz clock when I move it down. So let me pull it out. This big tangle of wires right here. I don't know if there's going to be room to get this in here. And the reset switch. I don't know. We might have to leave the reset circuit where it is. Things don't always work out the way you plan, you know? Not until you start, hey, that power, that plus 5 volts is in the right place. Let's put in a ground line for it. Okay, and let's see, this isn't needed anymore. This isn't needed anymore. This is way too long. That's way too short. Let me replace the clock line for the Z80 with something a little shorter. Okay. We'll test it out and make sure it's still working. I haven't screwed anything up. Well, I'm screwing up right there. That goes over here like so. Okay. Alright, let's plug it back in and make sure that much works anyway, huh? Make sure it's still gonna run. Yep. Alright, so we freed up some board real estate up here, which in a future video we're going to use to put the second clock oscillator in, the 1.8432 megahertz oscillator that we're going to use for generating our bit rate with the counter timer chip, which we're going to install in a future video too. So let's see, yeah, I don't think there's room to move the reset button down, so I guess the reset button's going to have to stay where it is. That's okay. Another thing, I didn't mention it earlier, but another thing I want to do, I want to pull out the LED for the M1 LED, because it's really not telling us anything at 4 megahertz. It's just like constantly on. So really there's no point in having that there, so we can pull that out. And it's going to appear in the level 1 schematic. Just ignore it. I didn't have a chance, you know, this is kind of a change I'm making on the fly here, and I didn't get a chance to update the schematic. You can leave it on if you want to. Hey, do whatever you want with your own version of this machine, alright? You don't have to slavishly copy me. You can do your own thing. Okay, so since we're not redoing the reset button, I guess we can move right on to changing this out. Let me unplug it again. It shouldn't be working on it plugged in. That's bad. Bad form. So, as you can see, I have a zero insertion for socket here, which makes getting your EEPROMs in and out of the board dead easy, simple, quick. You don't have to worry about lining up the pins every time. You don't have to worry about messing up the wiring when you're trying to take it in and put it out. It's dead simple and quick and easy, and I would highly recommend this because we're going to be replacing this chip a lot. Every time we tinker with the firmware, write a test program, whatever, we're going to be popping the chip out, reprogramming it, popping it back in. This could happen hundreds of times. This socket will make your life a lot easier. Now let me pull this socket out though and show you something. Zero insertion force sockets come with really chunky, short pins, which really means they're not going to go into a breadboard. So what you need to do is just need to solder some straight headers on them. And that's what I've done here. I've soldered some headers on it so that they're nice and long now. They go into the breadboard easy. They stick up above all this wiring mess. Makes life a lot easier. So that's what I recommend you do. Get yourself a zero insertion force, solder some straight headers on it, and boom, you're in business, okay? Let me show you something. Here's what we've been using. The 28, well, it's a 2716, but we've been using a 2816. Pretty much the same pinout. We're going to a 28C256. So as you can see, not only is the pinout different, but the 28C256 has 4 more pins on it than this one does. Now, if I had been thinking ahead when I built this thing originally, I would have wired it a little bit differently. I wired it with a 28-pin socket. This is a 28-pin socket, okay? So that's good. But I wired it so that the chip is sitting forward in the socket. I should have wired it with the chip sitting backwards in the socket, because towards the back of the socket, because that would have made things a lot different. Because if you notice, you know, from here forward up to here, the pinout's pretty much the same, and there's very few changes that need to be made. It's only in the 4 unused pins that would need to be changed. So, but I didn't do it that way. So that basically means I'd have to move pretty much every stinking wire on this thing, okay? Or maybe, just maybe, I don't know if there's room to do it. These wires are pretty tight. If I could slide this 2 spaces over, further that way, that would save me a lot of effort. But I don't know if I can do that, because this is just all this wiring coming through here, and it's all so tight. I don't know. Let me see if I can do it without breaking anything. If not, I'm going to start pulling wires out and rewiring everything. Okay, so I've been very gently prying and moving wires here, and I think I can do it. And please pardon the sniffing and the throat clearing. I've still got a little bit of post-COVID crud going on with me, which is one reason why I'm inside working on such a beautiful day rather than outside working in my workshop, at my foundry, whatever. You can see that kind of stuff on my main channel. This might just work. As long as I haven't broken anything, I might be able to just push this down in there. Okay. Alright, so now I'm just going to have to rework a few things. Let's see. But not that much. Not that much, really. I'm going to have to rework power and ground, because they're going in the wrong place. Let's see. I got to pull up right enable. I got to get A12 and A13 to it. A14 we're pulling to ground if we look at the schematic. because we're only going to use the lower half of this chip. Although we have the option of I could put in a switch or just a jumper, and if we wanted to use the upper half, we could. We could have two different programs in this EEPROM if we wanted to, and we could just select which one we want to run when the machine boots up. So that's a possibility, but for now we're going to tie A14 to ground. So okay, so let me get to work here. Let me swap some things around, move the power, the ground, get A12 and A13 to it, ground A14, and then double check that everything else is still right. Okay, so let me get to work. Okay, I spared you about 20 minutes of me very gently moving wires around in here, trying to get everything the way it is, and I couldn't even get the read line. I had to pull it off of my I/O decoder way up here. There's just no way to get down to pin 21, so I pulled it off of there. Let's see, I've got power and ground. Let's see, where's my cheat sheet here? So I got power and ground hooked up on it. The right enable is pulled up. 13 and 12 are brought in. They're over here. And I think that's everything. Okay. So over here we've got the 2716 that was in here, the 2K by 8. And I've got a 28C256 EEPROM here, 32K by 8. So we're going to put it in and give this thing a smoke test. See if it still works. It was working on this before I started messing around with this socket. So let's see. Plug it in. Okay. Power it up. And hey! Alright, I did it all right. So we're still working. And the program I have in here, it's kind of complicated because, you know, the Z80 is running at 4 megahertz. And to make these LEDs sequence back and forth slow enough for you to see it, there has to be a delay loop in there. And what I did was I created the delay loop as a subroutine. So to call and return from subroutines, you have to have a stack, which means you have to have RAM. So I set up a stack in RAM, and then I can call and return from subroutines. And basically this program not only tests that, well, that the processor's running, it's reading from the EEPROM, it also tests that the RAM is still working, and my I/O is still working. So I kind of, with one simple program, I can test a lot of different stuff and make sure it's all working. So that's great, it's all working. Now speaking of programs, if you go to my blog, there's some test programs there that I wrote. This program in here is one of them. It's called Fast LED Scanner, and fast for fast clock. There was a slow LED scanner, or just LED scanner I think it was, when I was on the 555 clock. That didn't have any time delays, and I'll tell you what, if you run the regular LED scanner program at 4 megahertz clock speed, all these LEDs are on. You can't tell that they're sequencing back and forth at 4 megahertz just because they're going so fast. So you have to use the fast LED scanner program at 4 megahertz and you'll get this pattern, and it'll also get a RAM test that way. You'll get an I/O test. Everything is working, okay? Also, there's a RAM test program, a specific RAM test program there. And I think we'll spend the rest of this video, rather than tackling some of the other stuff like I need to redo the I/O address decoding, I need to swap out this chip for a different one, I need to take this stuff out because we're not going to be using it anymore. So rather than tackling all that in this video, I think we'll leave it to the next video, and we'll talk a little bit about the software that I'm using here, how I wrote it, how I compile it, how you can do it, cheap, easy, and for free. If you want to write your own software, rather than just going with my software that's already pre-compiled for you as Intel hex files. I'll also talk a little bit about how I program the EEPROMs, what sort of programmer I use, and where you can get one too. Alright, so let's do that for the rest of this video. I'm pretty happy that we've gotten this far on the hardware without breaking anything. Yay. I'm going to clean up the mess I've made on my bench, most of which, fortunately, is out of the camera's view. So, on my blog, I have links to all of the stuff, you know, needed to build the JAZ80. There's a link to that in the video description, so you don't have to worry about this big long link up here and typing it in. Just go to the video description. Down at the bottom underneath this video, there'll be links to everything. So on that web page, there's schematics in both PDF and KiCad format. There's the bill of materials, and there's example code. And the example code here, this is my fast LED scanner. This is the program you've been seeing running on the machine for the most part during this video. And it basically just scans back and forth across those 8 LEDs on the diagnostic port. And it's kind of a little complicated program here in assembly language. It introduces some, if you're new to assembly language, this is going to introduce some new concepts to you. We'll go through it really quick. This is not meant to be a complete tutorial on Z80 assembly language programming or assembly language programming in general. Maybe we can do some videos on that in the future. But I'm going to go through this fairly quickly, and hopefully you'll get the gist of it. Up here at the top is an origin statement. The origin of the code is at 0000 hex. So basically at the bottom of memory, which is where our EEPROM starts. We're going to initialize a stack in this program, and I am setting some equates here. Basically, these are variables. Stack start, port address, delay count, these are variables. And we're setting variables with the equate word here. We are setting these variables to these values. So we're setting stack start to 0000 hex. We're setting port address to 18 hex, and we are setting delay count to 7FFF hex. And you might be wondering, if you're a little familiar with this, why I'm starting the stack at 0. We want the stack at the top of memory, which is FFFF, right? Well, the first thing the Z80 does whenever you do a push onto the stack is it decrements the stack counter. So first thing you really need to do is initialize this to 0000. First time you use the stack, it will decrement the stack pointer to FFFF. So that's why we're starting that up there. Port address, I'm thinking ahead here because that's going to be the address of our port once we get to level 1, level 2, level 3. Our diagnostic port will be at 18 hex, okay? Right now at level 0, any write at level 0 goes out to the diagnostic port right now. But once we get to level 1, we're going to have different I/O decoding, and the diagnostic port's address is going to be 18 hex. So we're putting that in there. It's still going to work with level 0 software because any write, like I said, to any port is going out to that diagnostic port with level 0 hardware. Delay count, we'll talk about that in a bit. First thing we're going to do is initiate the stack. We're going to load the stack pointer with stack start, which is up here, 0000, okay? And now we've got the actual body of the program here. What we're going to do, I call this part, just kind of came up with some arbitrary names for different sections of the program, and we move through the, from one section to another. We're going to start up here. We're going to load the A register with the value 1 of hex, and we're going to clear the carry bit. And there's really no command in the Z80 to clear the carry bit, but if you do an OR command with basically OR the A register with itself, that will clear the carry bit. You can OR it. You can do a couple of other things, math functions, and that will clear the carry bit. So we need the carry bit cleared for what we're going to do next. First, we're going to write the value in the A register out to the diagnostic port. So it's going to write a 1 out there. We're going to call delay. So we are calling a subroutine here. And this is why we need the stack. When we call delay, the address of where we're leaving the program flow here is going to get pushed into the stack. And then we're going to come down here to delay, and we're going to run through this delay routine. And when we're done, when we hit this return function, the address of where we left off up here before we called delay is going to be pulled off of the stack. So we need the stack initialized in order to call and return from subroutines. So we're going to call delay. We're going to come down here to the delay subroutine. We're going to push the AF registers onto the stack to preserve them. We need to preserve the number that's in there because we're about to change it. We're going to load the HL register with the delay count, which is up here. We have set it to 7FFF. That's the delay. We're going to decrement the HL register. We're going to load A with the L side of the register, and we're going to OR it with the H side of the register. The only time this will ever come out to 0 is if both the H and the L registers are 0. Otherwise, it will be something other than 0. We're going to jump relative on not 0. We're going to look at the 0 flag, and if it's not 0, we're going to go to loop. So we're going to come boop, up here, and we're going to decrement the HL register again. And we're going to keep doing this. Decrement it, check to see if it's 0. If not, loop back up and keep this up until we count down through 7FFF down to 0. That's going to take a little bit. And then once this actually hits 0, well, we're not going to jump on not 0 anymore. We're going to blast right through this line and come down here. We're going to pop the AF register off the stack, restore it to what it was, and we're going to return. And this is going to take us right back up where we were. So now the next command here is rotate left A. So we're going to basically rotate the bits in the A register one space to the left through the carry flag. And then we're going to check the carry flag. If the carry flag is now set, we're going to jump down here to swap. But if it's not set, we're going to go back up to up. And we're going to start over again. We're going to output the value in the A register to the diagnostic port. And now what we'll see is the next bit over will be lit and the first bit will be out because we've rotated that one we started with over one position in the A register. And then we're just going to keep this up. We will call delay. We'll go down here and we'll kill some time because, you know, our brains don't work as fast as the computer does. So we have to have a little bit of delay so we can see that the lights are moving. Otherwise, they'll all just look like they're on if there's no delay. When we come back from delay, we'll rotate left again through the carry flag. We'll check the carry flag. And, well, again, the carry flag won't be set because now we've only moved 2 positions over. Well, we need to move all 8 positions over before the carry flag is set. So this is we're going to go through this 8 times. And then the carry flag will be set. And then instead of going back up to up, we're going to jump down here to swap. And what we're going to do here at swap is we're going to load A with a different number. We're going to load it with 80 hex, which is basically the far left light is on now, and all the rest are off. We're going to clear the carry flag with our little trick of ORing the A register with itself. And then we're going to start counting down. See, up counts up, down counts down. And we're going to start counting down. We're going to output the number to the diagnostic port again. So the far left LED will be on. We're going to call delay. We're going to come down here, kill some time. Come back up here. What we're going to do is now we're going to rotate right through the carry flag. We're going to rotate the value in the A register to the right through the carry flag. We're going to check the carry flag. Well, carry flag's not set yet because we got to do that 8 times before the carry flag's set. We're going to go back up here to down, and we're going to do all that again. And we're going to do this 8 times, and finally the carry flag will be set. Oh, okay, carry flag set. we jump up to top and we start all over again. So this is how the bits and the diagnostic scan from one at a time from right to left and then back from left to right and then just repeat endlessly. This is how this program works. I hope that's kind of understandable. I hope my explanation is kind of understandable. Let's take a look at one of the other programs. So here's the LED scanner program. We've talked a little bit about how I wrote it, how it works, how it uses a stack in RAM, how it uses a time delay to slow things down. So, but we got another program we can look at here. So let me turn this off. Let me pull this chip out. And I've programmed up another 28C256 with my RAM test program. And let me zoom in on the LEDs over here, these green LEDs, so you can see what's about to happen. It's going to be quick. Let me turn it on. And there it goes. See how quick that was? We just tested the upper 48K of RAM. Let me run it for you again. I'll press the reset button. So what's happening here is the program is starting out at just above the first 16K, and it is incrementing all the way up through FFFF or 64K. Actually, it's going to increment until it gets to 0000, and that is when it knows it's reached the end of memory and it's wound up back down at 0 again. So it's very quick at 4 megahertz. And what we're looking at here on these LEDs is the upper 8 bits of the address lines. And just sort of a visual indication of what it's doing. And what it's doing is it's writing 2 different values to each RAM location in here and then reading them back and making sure that it's reading back what it wrote. And if it gets all the way to 0 and there are no errors, it gives us a 1 on the output. And if it was to hit an error anywhere along the way, it would stop and it would put FF on the output. So all these LEDs would be on basically if it found an error. When it gets to the end of the program, it halts. It issues a halt instruction, halts the CPU, the halt light comes on. Just a good visual indication that the program has executed all the way to the end. We can look at the code of this one and go over it too. So here's the RAM test program I was telling you about. It's actually a pretty simple program. We've got the origin line up here again, where the origin is at 0000 again. We have some equates. Again, these are variables we're setting up. RAM bottom equates to 4000 hex. That's going to be just above the EEPROM in level 1, level 2 systems. So we're not going to bother trying to test the RAM lower down because we'll be looking at EEPROM and not RAM, and we will get an error message because we can't write to that because the EEPROM is not going to be writable in this system. And again, the port address, we're looking ahead, it's going to be at 18 hex. So what we're going to do here is we're going to load the A register with 00, and we're going to output that to the diagnostic port, so all the LEDs will go out. We're going to load the HL register with RAM bottom, which up here is at 4000 hex. As we come down here, we got a little routine called test here. We're going to load A with the contents of the H register, and we're going to output that to the diagnostic port. We're going to load A with 55 hex, and we are going to write that out to the RAM address in the HL register. We're going to load A with the contents of the RAM at the address of the HL register, and we're going to compare it to 55 hex. So basically, we want to make sure that we get back what we wrote. If we don't, we're going to jump to error down here, and error will write FF out to the diagnostic port. So all the LEDs will come on. If all the LEDs come on at the end of the program, then we know that there's been an error in testing the RAM. If there's no error, it's going to come down here and it's going to load the A register with AA hex, and it's going to write that out to the memory address indicated by the HL register. And then it's going to read back the memory at that address, and it's going to compare it to AA and make sure we got back AA from that memory address. If it doesn't, it goes to error. If there's no error, it comes down here and it increments the HL register. So adds 1 to it. Then we're going to load A with the contents of the H register, and we're going to OR it with the L register, which is what we did back with the other program where we were doing the time delay. And the only time that this will be 0 is if both the H and the L registers are both 0. If they're not 0, we're going to jump back up here and we're going to do this all over again. And we're going to keep going through this and incrementing HL and going through it and incrementing HL until we get to FF in the HL register. The next time we increment it, it's going to roll over to 0, 0, 0, 0. And we come down here and we test to see if H and L are both 0, they will be. And then it will jump to OK. And down here at OK, it will write 0, 1 to the diagnostic port. So if the program ends with no errors, what we'll see on the diagnostic port is a 1. The rightmost LED will be on, and that's it. And then either way, whether we have an error or we don't have an error, next we come down here to exit, and what exit will do is issue a halt instruction, which will stop the processor from running, and the halt light will come on. And that's how this program works. I hope my explanation was understandable. So as I promised, I'll show you what I use for programming my EEPROMs. It's a model TL8662 Plus. I will zoom in on that for you so you can see that. I will also put a link to this in the video description. Now, this particular programmer just became obsolete. The company that makes it has come out with a new model, and they're not selling this one anymore, but there's still plenty of inventory of these on places like Amazon. You can get them pretty cheap. You could also pick up the newer model, which I would recommend because it's supported with updates. So probably, I'll put a link to the newer model down there too. Now, if you look around on Amazon, you'll find a lot of people selling these programmers, and some are selling them cheaper than others. But be careful if you go with the cheapest seller, because a lot of them aren't selling all the accessories that comes with it. There's a whole bunch of accessories that come with some of these. You want those accessories, so don't get the bare bones unit without the accessories. Get one of the units with all of the accessories and adapters that go with it. Even if it costs you a few extra bucks, you'll be happy about that in the end. All right, it's got a pretty simple interface. Basically, you tell it what chip you're programming in this case, and it was an AT28C256. You load the file you want to program in, and you press the program button, and that's pretty much all there is to it. A few seconds later, you got a program chip. Okay. You can also read the programs back. You can edit them right here. If you're into bare metal machine language editing, you can edit the programs right here. I've actually had to do that a few times. And then reprogram it. So yeah, it's a fairly flexible program. You can do all kinds of stuff with it. So I don't know what the latest version of this, what kind of software it has with it, but I would assume it's probably pretty similar. It's just the controller's a little different, or it's just the programming end is a little different, and I'm sure it supports a whole lot more chips than this one does, although I just updated this with the latest version of the firmware for this, maybe the last version of the firmware for this since it's obsolete now, but it handles a godzillion chips. Trust me, there's not much I've found that it can't program. Okay, so like I said, there's links in the description of this video to the EEPROM programmers and everything else that I'm using to build this computer. So if you want to follow along at home, you can pick up the parts you need. Okay, I wanted to go over a few resources that are going to make your life a little easier if you get into this. There's a lot of stuff available online to help you out, and I will put links to all this stuff in the description of the video down below, and also on my blog there'll be a file with all these links to everything in it. You'll want to get a copy of the Z80 CPU user manual. This has everything in it, you know. Especially if you want to vary from my own design at all, you're going to need this. I mean, it has all of the timing, it has all of the instructions, everything you need to work with the Z80 processor. It's available in multiple places online, and this is just the beginning. I mean, this is just the first few pages. This goes on and on for 332 pages of everything you could possibly want or need to know about the Z80 CPU. And I reference this all the time, both when I am doing hardware, when I need to look at a timing diagram or something, and also when I am writing software. I will say, oh, what does this, how does this instruction work? What's the actual syntax? So yeah, this manual is very, very useful, okay? And there's also lots of manuals for the peripherals that we're going to be using, like the CTC, the SIO, the PIO, any of the other Z80 family peripherals out there. There's manuals for them, and I'll reference some of those manuals in the future when we get to working with those parts. But I just wanted to tell you that you can get the CPU manual. You can get it online. There is one place, Thomas Scherer's Home of the Z80 CPU official support page. I don't know how official really it is, but this has all kinds of good stuff in it. Hardware, software, utilities, facts, docs, all for the Z80 family. You can find just about anything you need here. I mean, there's code examples. There's all kinds of stuff here, including all the manuals for the CPU and all of the support chips. They're all here. So this is a good place to go to when you need something Z80 related. One section of this website is all on software development tools for the Z80 family. If you're going to roll your own software and not just go with my own examples here, you're going to need some software development tools. You're going to need to download like a cross compiler or something for your computer, or there are some online alternatives, and I really like the online ones. I use them a lot. There's this one here. This is called JAZ80. It's a Z80 online assembler. You just browse and select your source file, and then you assemble it. You know, it's got a few options here you can click, and you can assemble it, and it'll give you, you know, error messages if you've got problems, tell you what's wrong, fix them, try it again until you get something that assembles correctly. You can download the Intel hex file, burn it into your EEPROM, plug it into your own version of the JAZ80, and go to town. I really like the online versions of these because I don't have to get anything that's going to work under my current version of Windows, or, you know, just deal with all the installation and all that. I like the online versions, you know, and it has all kinds of options. You can use 8080 assembly syntax instead of Z80 if you're working on a different type of system. You know, comes in really handy. And the one I use most often is ASM80, which I really like this site. This is great. It's got a visual IDE type setup here where you can actually type in code. It highlights it, code highlighting, which is nice. You can compile it. See here, I'm working with the fast LED scanner program that I've been talking about in this video. And you can compile it. You know, compile it. It makes the hex file automatically. You can download the hex file, burn it into your EEPROM, and you're good to go. And there's just all kinds of stuff on this website. It's amazing. There's emulators for all kinds of different systems up here. They're fun to play with. And the fellow who runs this website actually sells some retro kits too, and they're fun to look at. But really, this website is an amazing resource. I use it as my main assembler, and you're probably going to see it a lot in this series. I just really like this website. So give this stuff a try if you need it. Certainly get the Z80 manual, maybe some of the other Z80 product family manuals, the CTC, the SIO, the PIO, those will come in handy in the future. And, you know, depending on how far into this you want to get, whether you just want to follow my example or if you want to, you know, branch out on your own, everything you need is probably right here on this website somewhere. And like I said, links to all this stuff will be in the description of the video and on my blog on the JAZ80 section. In the next video, I think we will tackle, well, we'll have to redo the I/O address decoding down here before we do anything else. So in the next video, we'll tackle that. Install the new crystal oscillator for our bitrate generator and put in Z80 CTC chip. We'll do some firmware writing to program the CTC once it's in there so we can get the bit rates out of it that we want. And then once that's done, in another video further down the line, we can install the SIO chip, the serial I/O chip, and it will have an output from the CTC that it can use, send and receive serial data. So yeah, I think that's what we'll do in the next video. So I think that's all for this video. Thanks a lot for watching. I hope you found it a little bit educational, informative, whatever. Give it a like, give it a thumbs up, and subscribe to see my future videos. Check out my main channel, Omega Geek 64. There's amazing stuff going on over there, if I do say so myself. And I will see you in the next video. Thanks a lot for watching this one. Bye.